For the last part of today's lecture, I want to take you back to sort of our first example um, that we used to sort of talk about integrals, right? And that's, usage rate of a function, right? So say we have some function um, that models, once again, the number of petroleum barrels that your country, company, whatever, is going to use over a course of time. And of course, I'm having trouble drawing a function that I'm happy with. That is a really good one, but it's green. Let's see if I can change it. I think style works. Oh, look at that. Cool. So let's say we have this one, right? We know that this area here um, is able to model, right, the total amount of petroleum consumed over time. Okay. Um, but here's one question that I have for you. What happens if you're trying to look at um, some other possibility, right? Maybe the country is considering passing some legislation that would limit the amount used. Maybe some new technologies develop that increases the efficiency, and so less is used. And the projected amount under this new possibility, we'll say that curve only looks like that. Okay, it's not quite flat, right? It's still increasing, but it's increasing way, way slower. Okay. Of course, we can take the integral and find the total amount of petroleum used, say for g of x. But one thing that we would most likely actually be curious about is the difference here. Right? What is the area between these curves over this interval? Right? And the obvious way to do it, right? Well, why don't we take the total, right, the bigger amount, and then subtract the smaller amount, right? The integral from, once again, we should give these names, call that A, call that B, right? Or why don't we just call this 0, because that's what it is, right? The integral from 0 to A of f of t, which I'll write that in red just because we have this nice color, dt, right? So all of this stuff. And then if we subtract just the area of g of t, so from 0 to b of g of t dt, right? Hopefully you can see that that would give you this area in here. But since our integral will split over some indifferences when the bounds are the same, of course, this is the integral from 0 to b of f of t minus g of t dt, right? That's sort of the core insight here that allows us to do it, okay? And, of course, this relies on some assumptions, right? That f is always bigger than g on our interval. Okay, that's sort of the biggest one. Um, and in this sort of process here, we're assuming that they're always non-negative. Okay. Um, you can show that this still works even if they are negative sometimes. Um, there's an exercise in the book where you show that. Maybe I'll assign it, maybe not. I haven't quite decided yet. Although I should add, I meant to say this in the first part of this lecture. Um, you should be getting an email on the day these lectures go out with this information. Homework 10, so the homework on this chunk of material will be optional, heavily recommended because content from this week will be on the final next week. But I won't, uh, force you to do the homework, um, but it is recommended. Okay. Um, but anyway, so this realization, right? This is going to allow us to uh, find the area of more complex shapes in the plane, right? Um, and the rest of this lecture is actually just going to be a series of examples going through different ways that these problems can be set up. And we can start with the simple one, or the probably simplest possible case that isn't a rectangle. I suppose, rectangles, triangles, those are simpler, but those were all covered by our previous work. Find the area of the region bounded by the x-axis, y equals negative x squared plus 4x minus 8, x equals negative 1, and x equals 4. Okay? And why don't we very quickly actually draw what this guy is going to look like? So we'll need this. It's going to have a y-intercept at 1, 2, 3, 4 here. It's going to have a vertex here. And this parabola is going to look like this. 8, 9, 10, 11. It should be there. This parabola is going to look something like this. And we're looking for the area bounded by this parabola on the bottom, the x-axis. So I'll put all of my other bounds in green. So this guy here. And then x equals negative 1, which is this line. And x equals 4, this line. Okay, so we're looking for this area right here. And since we, sort of think vertically with this is going to be the integral from negative 1 to 4 of, well, between my x-axis, which is going to be 0, right, because that's the larger function, minus this guy, so minus a negative x squared, so plus x squared, minus 4x plus 8 dx. Okay. And then from here, right, we can rewrite this from negative 1 to 4 of x squared minus 4x plus 8 dx. Right? This is the definite integral of a polynomial over a region. I'll let you sort of pause it right now, work this guy out, and confirm that you get 31 2/3 on that guy. Okay. But let's look at something that does a little bit more, right? Let's say bounded by, because we know we're looking for the area of the region bounded by f of x is 2x minus 1, g of x is x squared minus 4, and then we'll need two vertical lines, x equals 1 and x equals 2. Okay, so with these functions, it's often easiest to graph them before you try to do any algebra. And that's because the graph is going to tell you which function you should make, quote, the top one, right? So we know one of our lines is 2x minus 1. So we'll put some dots down and draw this graph. Right, so this is 2x minus 1. And then we have x squared minus 4. That guy's going to be minus 1, 2, 3, 4. Let's see what this parabola does. It's going to be there, and out 3. Square through, we get 9. Minus 4 is going to be 5, so 1, 2, 3, 4, 5. It's going to be here. They're actually going to meet at that point. Then we can draw our parabola like this. So x squared minus 4. And then we need the vertical lines x equals 1. So this guy. And x equals 2. So this guy. Right? We're looking for this little thin sliver of area right here. And we can calculate that. You have to go from 1 to 2 of, well, it would seem like my larger one is going to be 2x minus 1. So 2x minus 1 minus x squared minus 4 dx. But then that's going to be from 1 to 2. Looks like of minus x squared plus 2x plus 3 dx. Taking antiderivatives, this looks like to me it's going to be minus 1/3 x cubed plus x squared plus 3x. Right. We're evaluating from 1 to 2. When we evaluate at 2, looks like we're going to get minus 8/3 plus 4 plus 6. Then, of course, we need to subtract. Looks like 1/3 plus 1 plus 3. And counting all this up, we're going to have 11/3 at the end of the day. Okay. One thing that I want to draw your attention to here, though, is that we can do a little bit more with this graph, right? What if so find the area of the region. What if we just say enclosed by f of x is 2x minus 1, and g of x is x squared minus 4. Now when we take our graph, which we've already graphed it, so we can copy and paste it, now these vertical lines aren't what we're looking for. We're looking for the area enclosed between them, right? So, you know, these three curves, or these two curves, sort of separate the whole plane into a number of regions, right? There's going to be this guy, this guy, this guy, this guy, and this one in here. And, you know, clearly these guys on the outside, quote, are going to extend forever. And so we can't say that those are enclosed by these functions. We can say, however, right, that this area right here, this is going to be enclosed by our two functions. So what that means is we need to look for the points of intersection, right? Because we need to know here and we need to know here. So it's a little obvious where they are via the graph, but just to confirm that, we can set x squared minus 4 equal to 2x minus 1, which is going to come out to x squared minus 2x minus 3 equals 0. And that's going to factor into x plus 1 and x minus 3. So then, right, we have x equals negative 1 and 3, which are indeed backed up by our graph. Okay. So now we can sort of view this, right? If we're looking for these sort of, vertical lines, we can view it bounded by the vertical line at x equals -1 and the vertical line at x equals +3, right? Those are what are going to control our bounds, right? So we're going to get the integral from -1 to 3. Well, f of x is still my, quote, top function. We get x squared minus 4 dx. And we saw that our antiderivative here, right, is going to be -1/3 x cubed minus x squared plus 3x. But now our bounds of evaluation are different, right? We're going from -1 to 3. And so when we plug this in, well, looks like we're going to get -1/3 times 3 cubed is going to be -9. Sorry, this should be a plus. 3 squared is going to be 9, and 3 times 3 is going to be 9. And then we're going to subtract off -1/3 times -1 cubed, or 1/3, -1 squared, or 1, and then a -3. And this is going to come out to 32/3. Next, let's take a look at the area bounded by the region. So the area of the region bounded by. Let's grab f of x is x squared minus 2x minus 1. G of x is minus e to the x minus 1. And x equals -1, x equals +1. Okay. Once again, we'll want to get a basic graph of our situation. Our parabola is going to have a vertex at 1, -2. It's going to come up like this. Right, this is a little chunk of our parabola. I'm going to continue up this way and up that way. Our -e to the x minus 1 was going to have a horizontal asymptote at -1. So we can kind of draw that in. At 0, it's going to be at -2, right? And then it's going to do something like that. And then we're interested in the area from x equals -1 to x equals 1. So this little sliver here, okay? So we're looking for the integral from -1 to 1. My parabola is my larger function. And then we're subtracting e to the x minus 1, but of course that -1 becomes a +1 dx. Simplifying this a bit, we're going to get the integral from -1 to 1 of x squared minus 2x minus e to the x, all dx. And then from here we can take antiderivatives. We have 1/3 x cubed minus x squared plus e to the x. Yes, this should be plus e to the x all the way up here, right? Because we're subtracting -e to the x minus 1, right? And so this should be plus, and that's plus. And then we're evaluating this from -1 to 1, okay? So we're going to get, it looks like, 1/3 minus 1 plus e, right? That's our +1 case, minus a -1/3 minus 1 plus e to the -1. And so it looks like we have 2/3, right? A third and then minus a -3. this minus 1 and this plus 1 cancel. And then we're left with e and an e to the negative 1. Okay, this is our answer. If you're curious, this is going to be about 3.02 units. Okay. And, one thing that we've been doing this whole time is only ever looking at functions where one function is on top the whole time, right? One function is always greater, but that's not always the case. We can actually extend these ideas to other regions, right? So what if we were looking at the area bounded by f of x equals x cubed, the x-axis, and then x equals positive negative 1. If we graph this guy, what are we going to see? Well, we know the behavior of y equals x cubed. It's going to do something like that. And we're looking between positive 1 and negative 1. We're looking for this area. But notice the x-axis is, quote, on top here, right? It's the larger one, but it's the smaller one here. Okay, so what that means is we actually need to break this up into two, right? Let's call this guy region 2 and that region 1. And so what that's going to mean is we can evaluate these one at a time, right? R1 is going to be the integral from negative 1 to 1 of my larger function is 0 and minus x cubed, right, dx. Of course, that negative is going to factor through negative 1 to, so this should be 0, not 1, right, because we're only worried about this little sliver here. And so we're going to get x cubed dx. Evaluating this, we're going to get negative 1/4 x to the 4th between negative 1 and 0, which is going to be 0 minus negative 1/4, or 1/4. Okay. My region 2 is going to follow fairly similarly. We're going to have the integral from 0 to 1 of x cubed minus 0 dx, right, which is going to equal 1/4 x to the 4th between 0 and 1, which is 1/4 minus 0 equal to 1/4, right? And so then my area of the region is then 1/4 plus 1/4, or 1/2, okay? And of course, these can get more complex as well, right? Let's say find the area completely enclosed. Say f of x is x cubed minus 3x plus 3, and g of x is x plus 3. I'm going to give you a quick sketch of these graphs. They're going to come out to something like f of x is going to look like that, and g of x is going to look something like that, okay? So then, of course, the area completely enclosed is going to be the sum of these two, okay? And so what that means is we're going to have to do the same process, right? We're going to have to find these 3 points, right? Do my first integral here with f as the larger function. Do my second integral over this region with g as the larger function. But in order to do that, of course, I need to find where these actual points are, right? So I need to figure out where x cubed minus 3x plus 3 is equal to x plus 3. Now, of course, this is going to simplify a bit into x cubed minus 4x equals 0. I can factor out an x, and we're left with x squared minus 4. And then that's the difference of squares. So we get x minus 2, x plus 2. And so we can see we get x equals 0 and plus or minus 2. So that's going to tell me that those are the values of where these these two functions meet. -2, 0, and +2. Okay. And now we split these up into a series of functions, or into a series of integrals, right? My whole area, we can sort of once again break this up into region 1 and region 2, right? Region 1 is going to be the integral from -2 to 0 of x cubed minus 3x plus 3 minus x plus 3 dx, okay? Which is going to come out to -2 to 0, looks like x cubed minus 4x dx. Taking antiderivatives, 1/4 x to the 4th, looks like it's going to be minus 2x squared. No dx anymore because we've taken our antiderivative. From -2 to 0, okay, this is going to come out to 4, right? The 0 is not going to do anything. -2 to the 4th is going to be 16 over 4 is 4. And then we have a -8 there. The whole thing is going to be negative, and we have a +4. For region 2, the integral from 0 to 2 of x cubed minus 3x. This actually goes the other way, right? Because now x plus 3 is our larger function. And we're subtracting from that x cubed minus x plus 3 dx. This is going to simplify the integral from 0 to 2 of minus x cubed plus 4x dx, okay? Which is going to come out to minus 1/4 x to the 4th, and then plus 2x, evaluated between 0 and 2. And this, funnily enough, is also going to come out to 4, which means our total area is 8. And with this last example, that's going to wrap up these lectures. So I will see you on Thursday for the last lecture of the quarter.